looks good?
Yeah, I can see it. Oops.
Okay.
Okay. All right, everyone. So we're going to begin. So thank you for joining us for the fourth seminar of the Plant Phenome Journal Monthly Webinar Series. My name is Steve Anderson, and I'm a PhD student with Dr. Seth Murray. He is currently away for a funeral within his family in Michigan, so he will not be able to be here today. So I'll be moderating the talk today. So this webinar is the fourth in a series sponsored by the Plant Phenome Journal. We've had past speakers including Dr. Carolyn Lawrence Dill, Dr. Jesse Poland, and Dr. Chris Top, some of which have been successfully recorded and can be found on the website. And hopefully this one will also be recorded and be up there as well. So next month's seminar on January 8th is going to be in the second Monday of the month due to the holidays, and will be the lead author for one of the Plant Phenome Journal's first papers, Mr. Ace Pugh and Dr. William Rooney's program discussing UAVs to develop temporal growth curves in sorghum and maize. So today we're going to have a presentation by Dr. Sindhuja Sankaran. She is an assistant professor in the Department of Biological System Engineers at Washington State University. She is already well known for her work in proximal and remote sensing UAV technologies for high-throughput crop phenotyping, and she received her bachelor's in zoology and her master's in environmental science in India, and a master's in environmental engineering from Iowa State, and her PhD in agriculture and biosystems engineering from North Dakota State. She worked in India, Thailand, and Florida before coming to Washington State, and today Dr. Sankaran will be speaking to us about optical sensing for high-throughput field phenotyping, important considerations. So if you are ready, we can start the presentation, Dr. Sankaran.
Yeah, thank you very much for a good introduction. And I'm just going to talk about optical sensing for high-throughput field phenotyping. So my focus will be basically on field phenotyping and important consideration, because quite often when people use sensing, there are some of the major things that they miss, and I just wanted to refresh everyone on some of those reminders as a part of this presentation. So just to give a brief background about agriculture in Washington, we have more than 300 commodities grown in Washington, and the major reason is diversity in weather conditions within the state, different soil types, irrigation types. In central Washington, we have Columbia River, which is very good for irrigated agriculture. And here in Palouse, we have big wheat and legume production. So we are ranked number 1 in more than 11 commodities, and the top commodities are apples, wheat, potatoes, cherries, grapes, pears, are some of those. Just to give a brief background about breeding program in Washington State, we have more than 15 breeding programs focused in the state, and this is not just Washington State University, but also several USDA ARS research facilities that are present in the state. So even WSU main campus is home to some, and in addition to that, there are research and extension center across the state which work closely with USDA ARS labs. Just to give a few of those, in cereal grains, we have wheat breeding program, barley and quinoa as a new alternative crops that we are investigating in. Legumes, big chickpea, dry pea, and lentil production in Palouse. In addition to that, dry bean. Also, we have dry bean breeders in USDA ARS labs. And horticulture, just to name a few: hops, potatoes, apples, pears, pear, cherry. And one of the things that I want to mention is we closely work with commodity commissions, both locally and nationally. So this gives an excellent opportunity for my lab in Phenom X. So we are working with several of those breeders. And the exciting thing about sensing is it is a technology, and the data processing or image processing that's applicable for one problem can be transferred and adapted to several other crops. So here are just a few. We have plant height, we have potato disease rating, chickpea yield potential and disease rating, dry bean water use efficiency in apples, disease rating for fire blight, as well as abiotic stress, calcium, and also recently we are focusing on 3D architecture. So basically what I see as sensing for high throughput phenotyping is linking genes to the traits. So we have this broad genetic diversity population and you extract the genomic information out of it, and the phenomic description is very important in linking the genes to the traits. So the more accurate we are, it's very important for variety selection with desired characteristics. And we know, depending on which crop we are talking about, it takes 12 to 20 years. So probably grains and legumes somewhere around 12 years. And when we go to tree fruit, it becomes 20 plus years before a variety can be released and marketed confidently. We know high throughput, like phenotyping in general, is laborious. So we have multiple locations, thousands of breeding lines. We need high throughput phenotyping technologies. It's expensive. There's a lot of labor going into phenotyping, and mostly it's undergraduate students in summer, hourly workers working in summertime, just maintaining the plots, acquiring the data that's needed before we can select a variety confidently. It is subjective. So, and we have talked to breeders, and sometimes even while working in high throughput sensing, we are often confused, like how are we going to relate the sensor data to a subjective score? So it is very subjective, and it can be emergence, can be flowering, disease symptoms. It's all visual ratings. Of course, these breeders come with expertise of several years of experience, and they have a good call for rating it, but for some reason, if a breeder is unable to participate in a field data collection, it is difficult, or the subjectivity increases between two people. So this is just an overview on how long potato breeding as well as pea breeding program can take, and you can especially focus on year 1 and year 2, where much of it is based on just visual rating, and the selection is 1 to 2%. So if you have 100 lines, probably you're just going to pick 1 or 2. And this is very low, and probably high throughput sensing technologies can enhance the selection rate or reduce the rejection rate, however we may want to see it. So for me, a high throughput phenotyping technology is non-destructive, high throughput automated crop assessment. And by crop, I not only mean by field traits as well as post-harvest quality traits as well. And the technology can, or the platform can be independent. It can be controlled environment, or it can be field-based platforms. I would like to mention in 2015, we had a Phenom X conference on field-based high-throughput phenotyping, where we had several of participants. And one of the interesting aspects that also came up was that breeders are interested in low-cost or rapid or accurate sensing. So they don't mind a high-cost sensing technologies that's highly accurate and can help them find out things that are otherwise impossible, or it can be relatively less accurate, very quick, very efficient. So they said at least 2 of the 3 traits are very useful in identifying the high throughput sensing technologies. So, and we have an understanding that in controlled environment, the correlations are much higher than field conditions for obvious reasons, that in field, the control of environment can be challenging sometimes. So with that, we are using high throughput sensing technologies, mostly focused on visible, a little bit on near infrared range. So we are using visible near infrared spectroscopy or spectral reflectance imaging, as well as the thermal infrared imaging as well. So, and as I told you, the focus is on not only on crop responses, but also the produce and product quality is very important. Though often, I wouldn't say often it's ignored. The focus is more on developing high throughput sensing technologies for crop responses, but we cannot ignore the fact that the product and produce quality ultimately decides the release of a given variety. So I am just highlighting some of the simple platforms that are used for high throughput sensing. One is portable handheld sensors, and in this it can be a sophisticated visible near infrared radiometer or a crop scan that can be used for capturing the reflectance. So the benefit is you can get a reflectance measurement throughout the season. It sees beyond our eyes. So we are limited to visible range, but these sensors can see in the near infrared range. And based on literature in general, there are several publications that show that this data is very reliable. The limitation is low throughput. You can ask any graduate student trying to do this kind of research that they are exhausted by the end of the day. And it is subject to background noise. So if the canopy vigor is pretty low, for example, using crop scan, you're probably capturing some of the soil as well. And sometimes, which I'll talk later in this presentation, you may have a saturation in leaves. Some of the leaves surfaces are shiny, so that can be saturation, which also could be considered as a noise. Next is the customized tractor or a gator with a mast. This is two of the platforms that we are using in Washington State University, but there are several sophisticated, interesting platforms across the nation. For example, Kansas State University, University of Arizona has their own platform, University of Nebraska, Lincoln. They all have these, Iowa State University, all of these have sophisticated platforms that are used for sensing, mostly focused on a specific crop. So it's very high throughput, high payload. We have a LiDAR system. The entire system can weigh around 15 pounds. So we can put it in a ground-based platform. And you can get a georeference data if you tag it with GPS. Of course, limitations, system vibrations can affect the sensor quality. Terrain conditions are important, and long-term use may result in soil compaction and other issues. And the most exciting and the most interesting one is the unmanned aerial systems or drones. There is operational flexibility, and we have done that where in dry bean, when the canopy vigor is pretty high, it's very hard to walk through the field because these are tiny canopies. So we can use a drone to comfortably get a high resolution data. Even after irrigation, after a rainfall event, the operational flexibility is pretty high. You get a high resolution data, centimeter, sometimes depending on the altitude you're flying, you can even get millimeter resolution. And of course, it's high throughput. It's very high throughput. It hardly takes 15 minutes to capture an acre or two. Payload limitations, so you have to pick your sensors carefully, and you cannot put a LiDAR, for sure 2D LiDAR systems, but there are 3D LiDAR systems and hyperspectral cameras available for aerial applications. And it is environmental conditions play a role. If it's a very windy conditions, then probably you are going to drain your battery, and maybe drone or unmanned aerial system is not safe. Instead, probably a tractor may be a better system if the field conditions are always windy. I cannot ignore the fact that the drone base gives a very high resolution data in comparison to aircraft and satellite images. Though aircraft images are still used for phenotyping with decent resolution, you can get a higher resolution than 2 meters per pixel for sure. But you have to remember when it comes to phenotyping or breeding, the plot size can be pretty limited. There is a new era of nano satellites in these days. So these are latest technologies, and I am thinking in future the nano satellites are going to be more prevalent. It can give a sub-meter resolution, probably still suitable for breeding applications. Already we have several of these satellites in the sky. So they have near infrared stereo and video capabilities. One of the challenges was every 2 weeks you were getting data from the satellites, but some of these nano satellites are this low orbiting satellites that probably can fetch you sub-weekly data for your specific applications. And couple years back I was in a conference, Precision Ag Expo, and we had several of these nanosatellite companies participate in it, and what they told is their target market is agriculture, so which is a good news for us, and they want to make it available at a very low cost, probably $1 or $2 per acre is their goal. Of course, their market by meaning agriculture does not mean for high throughput phenotyping, but precision agriculture where they are trying to monitor thousands and thousands of acres of production. Limitation is it's still a developing technology, and in your left you can see some of the images that I downloaded from SkySat, and I think it looks pretty interesting and very good resolution, but we still need to let this technology develop further before we can use it for phenotyping application, but I feel this is going to be the future. And then there is a new era of sensors. There isn't a day that goes by where I am excited about a new sensor that is available in market. So there are several of multispectral cameras that are available, and some of these filters can be customized based on our needs. So if I'm looking for a specific near infrared wavelength, I can probably custom order it. These are some of the examples. The green one, multispectral camera, is Centra, and the middle one is Mikasense, and the right is the TetraCam. And not only the multispectral cameras, even the hyperspectral cameras are developing. So there are nano and micro hyperspectral cameras provided by Headwall, and their goal is to make it light enough that you can put it in an unmanned aerial systems. And I was talking about the 3D LiDAR, and Velodyne has a 3D LiDAR that is possible, like it is possible to mount it in an unmanned aerial systems. Of course, the resolution is still low. I'm not sure how applicable it is for row crops or grain crops. Probably it's best for tree fruits is what I would think. And sometimes you don't even need a LiDAR system to be able to reconstruct the 3D architecture. We can do that just using an RGB in drone to do the reconstruction and create a digital elevation model to be able to see your plants or trees. Again, as I told you, the technology is developing, and this is just an example of thermal infrared imaging systems. The nursery crops, you can see out of the 100 that there are 12 that are water stressed, which otherwise you cannot see in visible imaging, but you can clearly pick out from thermal imaging. Again, you can spend 60 to 100,000 in a thermal camera or you can use a lightweight, low-cost thermal camera. So we have this Adreno-based thermal cameras that are becoming more available in market, which is as low as $40 to $100. They are very low cost. And of course, the one which we mount in drones are FLIR 2 cameras, which can range from $3,000 to $8,000, and with the radiometric calibration is something that is needed to get pixelated temperature data. I thought I'll just touch base with one or two case studies before I move on to the important consideration aspect of this presentation. So in this work, we were focusing on chickpea and dry pea. We had both advanced and preliminary trials, multiple checks. We have been doing this for 3 years, but this is just a year's data that I'm summarizing over here. The experimental design was complete plot design, and that's the dimensions of each plot were 1.5 to 6.1 meter. And we did at multiple locations, Pullman as well as Genesee, and our trait that we were very much interested in this trial was the seed yield. So we used unmanned aerial system, which was a German-made microcopter Optical, which is a very pretty sophisticated system. We used multispectral camera, green, blue, and near infrared. We did image multiple times of the multiple days, so 60, 70, and 90 days after planting, around 110 above ground level, and we processed all the images using ArcGIS. We extracted two major features. One is the normalized difference vegetation index as well as green NDVI, which I'll just talk in a minute. So this is what a normalized difference vegetation index refer to. So what happens is, healthier the plants are, they will absorb more visible light and reflect more near infrared. So we think that just higher NDVI means the plant is able to absorb more visible. That means reflecting. So you can see that 8% red over there. So that means the healthy plant is reflecting less of red. And just by looking at NDVI, it can tell generally about canopy vigor as well as the greenness. So we can say that the greenness is related to chlorophyll content, the chlorophyll content is related to photosynthesis. So that's a general trend we are looking at, and this is just an example of what an NDVI is. So if we, instead of red, we replace it by green, we find that is a green NDVI. And in general, not just based on this study, based on all other crops we have worked with, we feel that GNDVI is as good as NDVI. So this is just a quick picture at 68 days after planting, at 68 to 72 days after planting at two locations. I should say that the red marked ones are actually chickpeas, and the more yellow ones are
phenotyping, they were not invited to.
Dry pea. So what we did was we did radiometric correction. Again, the importance of a radiometric correction, I'll talk about in important considerations. We extracted NDVI and GNDVI images, and what we did was we set a buffer zone in each plot. So the edges, we had a buffer in the edge zone and extracted the average NDVI from the center of the plot. Just a quick example. So that's a corrected original image, an NDVI image, and we do a polygon of each plots, and then we set a buffer zone, and you can see that the buffer one does not include the entire plot, and then we generate the statistical parameters. We find that the NDVI sum as well as mean NDVI sum is sum of all the NDVI, all the points, all the pixels, NDVI pixels in that plot. And also the mean, we get a very good correlation with yield potential, at especially at 68 days after planting. So this is the correlation with mean NDVI, and you can see that it enhances up to 72 days, and there is a very good negative correlation as well with the yield potential. So we find that the early maturing ones with low NDVI have a low seed yield, and I'm sure a plant physiological aspect of it, we can explain this. Just another example on evaluating growth factors in potatoes. So this was a study where they were intentionally adding growth regulators to get an early or delayed maturity. This is important for potato because you want potato throughout the season to mature, or a fresh potato throughout the season rather than all being harvested within a month. So you want the range for harvest period. And the way the horticulturists were evaluating this was counting the number of plants that emerged out. So they were literally counting, and what we did was we did an image-based count. We fly very low at 15 meters, and we found a very good correlation. Of course, when it reaches the canopy closure, it's very hard to count, but still, especially in the early stages, we can count confidently. So I'm going to talk for next few minutes. I'm going to talk about important considerations. The first aspect is radiometry correction. So whenever you use a multispectral camera, hyperspectral camera, or even RGB, the standard digital camera, what you're looking at is a reflectance. So what it means is the light shines on an object and it is reflected back. That is captured in an image. So often one aspect that is ignored is what is the light that is incident to an object. So if you're imaging a wheat plot, you want to know what is the incident light that is falling on the wheat before you can capture the reflectance. And there are ways to correct it. One standard way of correcting it is using a calibration panel or reference panel. Just a 2 centimeter circular reflectance panel can cost around $500. So it's very expensive because it is considered sort of a golden standard for doing radiometric calibration. So this is something sometimes people ignore, that if you want to capture the reflectance, it's better to do a radiometric calibration to know what is the incident light that is falling on the object. Okay, it's just one good company that sells the reflectance material is Spectralon. LabSphere sells it, and you can see there are 2 root images. One is without calibration, the other with calibration. This was a study where we were trying to estimate the root color because we were trying to rate the Phenom-X infection in lentils, and it's a root disease and it affects the root color. So you can see if you do not have that calibration panel, your light quality will greatly affect the image. But even if the quality of light is bad, somehow you can fix it using a calibration or reference panel. So that is one way of correcting it, both in controlled environment and field conditions. The second way of correcting it is using an incident light sensor. So what a incident light sensor means is it measures what is the incident light. So this is a very commonly used method in drone-based application where you have this light sensors facing the sunlight, where you know what is the incident light intensity. And you know, like if it's morning or evening, the sunlight intensity can be lower than midday, so it can help correct, or even if it's a cloudy and gloomy day, then your sunlight intensity is going to be much lower. So this incident light sensors corrects for incident light conditions. So it's called as upwelling and downwelling. So the light that falls on the object, it measures, and then it measures the relative reflectance related to the wavelength of the sensor. So these are the two common ways in which you can correct. You can do radiometric correction for both for field applications. The second aspect I wanted to touch base is that it's always better to open or split the image into their respective channels. Here I'm just showing an example of R, G, and B. The reason I'm saying this is sometimes you have this shine in the leaves, and those shiny surfaces is sort of reflecting 100% back. So what it means is when the leaf with a shiny surface is reflecting back, it's showing 100% reflectance, or the band is saturated already. So and not just because of a shiny surface, sometimes it could be because of the sensor setting as well. So even not just in reflectance studies, but also sometimes if you're interested in looking at colors of seeds or something like that, you want to make sure that it is not showing 100% reflectance, or else your data is already lost over there. And I think the best way of checking it is you can use a free software like ImageJ to split the channels, because sometimes it does not affect all the channels equally. Only one channel may be saturated. Here I'm just showing an example of R, G, and B, red, green, and blue. And I'm talking about an ideal scenario. A green plant will reflect more in green band. So that it appears green because it's reflecting more green than red or blue. So in general, the green will be slightly brighter than the red and blue bands. That's one aspect. And if you have a near infrared, often near infrared is the brightest image. If your near infrared is not the brightest image in your multispectral images, something is wrong. So either you have to do radiometric calibration, or surely something is wrong. And you have to pay attention to the saturation, because once you have a saturated data, means I have a lot of values at 255 range. When I do an NDVI, then it does not make sense to do an NDVI. Already one band is almost a constant. So that's something often I see being missed when we process the images. So that's something that we need to consider. Of course, I also wanted to talk about shadows. Shadows of one leaf within falling on another leaf is something that surely we cannot avoid. So, and there are image processing techniques like k-means clustering, by which you can eliminate some of those aspects. But surely we can avoid saturation by changing your sensor settings. So the next aspect I want to tell you is about for example, NDVI, right? So it's near infrared minus red, near infrared plus red. When you say near infrared, the near infrared has a very broad range. So it can be 700 to actually 2500 nanometer, but no one is going to sell you beyond 1000 nanometer because the sensor is going to be very expensive. So it is a range. So why I want to say this is, if you have two multispectral cameras, you cannot assume that one NDVI is same as the other NDVI, because the near infrared band in both the cameras can be completely different. So that's something that you need to pay attention to. Is first thing is to know what is the wavelength. So if you have a near infrared, if someone is selling you a multispectral camera, you need to know what is the near infrared band that they are providing. In general, we find that red edge, if the near infrared is close to red edge, they are very good in picking out some of the stresses. Another aspect is also the width of the peak is as important as the peak itself. So it's not one line. So if I say 700 or 800 nanometer, the sensor is not just capturing 800 nanometer. Usually it comes with a range. So either 750 to 850 nanometer, then they say 800 is the peak, right? So there is a range. That's something, again, something that you need to pay attention to. The broader the peak may dilute some of your data. So please pay, if you're purchasing a multispectral camera, this is something that you should know. What is the wavelength and what is the quantum efficiency? The second thing is the field of view. The field of view is, a sensor company may say, oh, it captures 2 centimeters or 5 centimeters. But 5 centimeter at what altitude is very important. So of course, when you go fly a drone or unmanned aerial systems up high, it's going to cover a larger area. But not all sensors are the same. And even the format, what is the megapixel, dictates what is the resolution that you're going to get. So there's another aspect that you need to consider is the ground sampling distance, so the distance between pixel centers. In general, based on our experience, in field, lentils are the smallest crops that we have worked with. So either we have to fly very low to be able to see lentils, especially in early growth stages, while for potatoes and other tree fruit crops, you can fly up higher. But that is important because especially if I'm working in legumes, I need to make sure that I get a very good quality data with the sensor that I am choosing. Another aspect is the inbuilt sensor and also the camera lenses. So you should know that higher the focal length of a camera lens, you're going to get a higher resolution, but your field of view is going to decrease. And that's always the case. So with higher focal length, you're going to get better resolution, but lower field of view. And we all often struggle this with our thermal camera, where you want to get a good resolution at the same time be able to cover many plots in a single image. Challenges is sensing can be affected by weather, especially visible near infrared imaging. Lighting and angle is very important. You cannot go in a very cloudy day and trying to capture the NDVI data. Light is important. The better the lighting conditions, the better it is. But sometimes we find that gloomy days are very good, especially if you're just looking at crop area. So we say, okay, you have relatively uniform light conditions. The background subtraction becomes easier. There is no saturation. So it does depend on your applications. And even for thermal data can change dynamically just by a cloud cover or a swift of wind. Your numbers can change drastically. And I think ultimately it is about utilizing the right tool for the right purpose at the right time. So the right time, in my experience for legumes, is somewhere at around 60 days after planting. so that 60 to 70 days after planting, almost the peak growth stages, we find that they are very closely related to seed yield potential. In potatoes, we find that early season vigor is very closely related to yield potential. Of course, our limitation is that the canopy, the NDVI almost saturates during mid-season. So that's something that you need to consider, that NDVI can saturate during mid-season. So you need to account for using the right tool for the right purpose at the right time. And also in plant breeding, there's always a variety differences versus stress response. So there may be early maturing varieties, late maturing varieties, long flowering period, like some of the varieties have long flowering days. So all those things could still be a challenge in getting what we want. Of course, sorry for the typo. I wanted to say big data over there. So the data analytics associated with remote sensing data is very important. So nowadays we have tons of sensors and we have people just collecting so much of data. Ultimately, we have to slow down and look what is the data analytics associated with capturing the data. I believe that with advancements in high throughput sensing, it's not only going to help crop breeding, but also plant biology research, agronomy, as well as precision agriculture and precision management. This is just a quick picture. This is an apple orchard in China where they were using a series of drones to capture the field. I would like to end my presentation by acknowledging my graduate students who have been working hard for their program and in field for capturing all the data. Dr. Laukoth, who is my remote sensing buddy or a colleague in this project, research scholars, visiting scholars who have been here and have been very productive, and a lot of breeders of different crops and collaborators who are there. So if I have a need, oh, I'm looking for this, I can reliably go to any one of them and they would help me either even develop a plot for my desired needs. And last but not the least, the funding agencies, especially USDA and NIFA program. We have a few projects funded by them, Washington State Department of Agriculture, and also we have emerging research issues, which is WSU Ag College internal grants that have supported some of this research. That, thank you all, and I'll be happy to answer any questions.
Okay, so thank you, Dr. Sankaran, for your exciting seminar and on the cutting edge area of optical sensing high throughput phenotyping. So we're going to have the next 15 minutes to have a few questions. There are two ways we can do this. You can write them in the chat, which is on the right side. You might have to activate it. And you can send it to me or to everyone, and then I'll read it, and Dr. Sankaran can respond, or in a minute you can unmute your microphone and we can take turns asking questions. So while you think about your questions, Dr. Murray has asked me to put in a plug for the Plant Phenom Journal. Remember that this is a Tri-Society journal dedicated to advancing these issues in high-throughput phenotyping and remote sensing. And they are still accepting articles at a reduced cost for a limited time for publication. So to begin, I have a question for you, Dr. Sankaran.
Yes.
So you work in a vast majority, a lot of crops. You work across a lot of disciplines. Mm-hmm. What have you seen that has that transitions across crops? Like what works method-wise or technology-wise, or have you ever ran into something where it works really good in, say, wheat, but then you take it over to the dry beans and it's not as good as you've seen it in wheat or other crops?
Yes, and that's a very good question. And that's why I had the last slide on using the right tool for the right purpose, probably for the right crop as well. So wheat is pretty good for remote sensing application. It has a very good canopy vigor. Sometimes we struggle that with legumes, especially smaller legumes like lentils. With dry peas, it still works. It's still, you can capture a very good data. That doesn't mean for lentil it doesn't work. But in lentil, if I'm going to fly a lentil plots, I have to fly lower to get a better resolution. So, and another aspect is, as I told you, like most of these legumes, I think including wheat, even cereal grains like wheat, we find that the mid-season data is the best time to capture the yield potential. In potatoes, it's very challenging to say that because it's such a vigorous crop that it saturates. And also, the way you plant is different for different crops. So sometimes you have to address that. So if I'm using a tractor for all crops, I want to make sure that I talk to the breeders and have their field plot design changed a little bit. And we are working towards it. Sometimes it's just enough for riding a tractor. So are they willing to change it a little bit? So of course, plot size you cannot change, but the distance between the plots is something that you can adapt. That still works best for them. Yeah, so I hope that answered your question.
Yeah, that was a good answer.
Yeah, and tree fruits are a completely different story. So.
Perfect, thank you. Does anyone else have a question that they'd like to ask at this time? Quiet group. Anybody? Okay, so remember you can, if you have a question, you can either unmute and ask or write down in the chat box. We still have a few minutes to ask questions.
Yeah, already sent on mail, means on chat. I sent 2 questions on chat. The one is...
Oh, okay. I don't think it came.
Can I go ahead?
Yes, go ahead. It didn't come through to me.
Yeah.
Sorry.
In the whole presentation, the traits he used was NDVI.
Mm-hmm.
So I'm interested to know what else trait can be used out of these images. One. Second, do you use only image pixels to conclude about these traits, or you also go for ground truthing to estimate? Say, for instance, if you are going for a specific trait like chlorophyll or say anything else, so means how this image being used to inference your observations? It's pixel based or also ground truthing too?
Thank you for the question. That was a very good question. So the reason I used NDVI is in the series of examples over here is it's a commonly used vegetation index. So I thought it could connect to the participants much more. But you're right. We do not use just NDVI. We have a series of multispectral cameras, and we use a combination of wavelengths to extract other features. Another good vegetation index that we found to be reliable was PRI, photochemical reflectance index. In addition to that, we also use the entire series from 350 nanometer to 2500 nanometer. We have a visible near-infrared spectroradiometer that allows us to do machine learning than just vegetation index. So sometimes we do supervised or unsupervised learning and then identify the spectral regions responsible for a certain trait. And we also have a hyperspectral camera that we haven't yet used in field conditions, but in the coming season we will surely use that as well. That's the first aspect of it. And what was your second question? Can you please repeat it?
Yeah.
Ground
Second
truthing,
was,
right? Yeah. Your second
yeah.
question was on ground truthing, if I'm not wrong. So as
Yes.
far as ground truthing goes, we also do a lot of ground truthing. Of course, not extensive ground truthing in all plots. We get a lot of phenological data, performance data from our collaborators who are mainly breeders. In addition to that, we have some of our own ongoing research where we use LICOR systems to look at photosynthetic efficiency, transpiration rates as well. So we use LICOR porometers to do our own ground truthing as well.
Thank you.
Dr. Sankaran, if you could, do you see in the top right corner where there's that chat icon? Is it blue?
Yes.
Okay, because I'm not seeing any of the questions come through on the chat, so I was
Me
just wondering
too.
if they're coming.
Yeah, I don't see it either.
Okay. So if you have a question, please, if you're putting it in the chat, maybe you have to go to send to Steven Anderson so I can read them aloud, or please unmute and ask your question.
Yeah. Hello, this is Pat Byrne. Can you hear me?
Yes, go ahead.
Yeah. And I'm wondering, how soon will it be able to do things like actually count spike number in wheat or get other types of quantitative measures like that in other crops?
That's a good question. And I haven't done spikes in wheat. And it could be challenging is what my understanding is. For the reason also, all the sensing technologies we are talking over here is only measuring at surface. So if anything that's hidden, shorter, then probably you cannot see. But I think recently we saw one study which was trying to look at the spikes and relate it to measurement, remote sensing measurement, rather than quantifying or number of spikes. So they were seeing if there was a relationship between an image processed image data and the number of spikes. Something related we are also attempting is to look at flowering dates. So we are looking at, okay, rate of flowering within a plot. And of course, you can count. Counting can be more challenging than if there is a close relationship between a processed image data and the flowering, rate of flowering in a plot.
Okay, so
Okay,
there
thank
is,
you.
I'm getting a few more questions in here. So here's the first one. In an RGB image, when you want to spot plants individually, how can you discard plant shadows from plants if unfortunately you still have shadows?
You can do image processing to eliminate some of those aspects, but that's something you surely can, you cannot do anything about it because the leaves are going to cast shadows on another leaves. But there are image processing algorithms that you can use to relatively control it rather than completely eliminate it. And quite often, sometimes in image processing, one of a primary step is a thresholding. You can play around with that aspect a little bit to eliminate the noise resulting from the shadows.
Okay, here's another question here from Renee. There are many vendors offering image acquisition and analysis as a service. Are there key questions researchers should ask vendors that would help them decide if useful data will be collected?
Can you repeat that question?
Sure. So, there are many vendors offering image acquisition and analysis as a service.
Mhm.
Are there key questions researchers should ask vendors that would help them decide if useful data will be collected?
Okay. So one of the questions, of course, there are questions like how often are they going to collect? How soon they will give the data? That's surely one question I would ask them is how soon once you collect the data, how soon can I get my data back is something. Another thing is if they are just going to give a processed image versus data, that's something else that I would be interested. Are you just going to convert it into another format and give me with different colors? Because sometimes colorful images mean nothing. So what is the quantitative data that they are going to give you? So if it's a series of plots, are you going to give me plot-wise data rather than just, okay, this is the NDVI image or this is a digital elevation model. So you want to ask what is the quantitative data and how soon you're going to get the data for sure. Another thing is what are the features you're going to get. So depending on your application, what is the features that you're going to capture. I would always get back my raw data. So if I would say like, okay, can you please, also, because you should be able to relook at them in case you want to in future. So that's something. Are you the owner of all the raw data that you're capturing?
Open up the next room on this subject slide.
Are there any other questions? I don't have any more in my chat. If you have one, please feel free to ask. Okay. If there's no other questions, I think we will wrap up this month's webinar. Again, I just want to remind everyone that this is a webinar series with the Plant Phenom Journal, and that we will be doing the next one on the second Monday of January after the holidays, where Ace Pugh from Texas A&M will be discussing the development of temporal growth curves in sorghum and maize. So please feel free to join us then, and we hope to see you there. And again, thank you, Dr. Sankaran, for your insight and your valuable presentation.
Thank you, Stephen.
Okay, thank you guys. Everybody have a great day and happy holidays.
Thank you. Same to you.